It's my honor this evening to give a talk to our EEE alumni. As Prof mentioned, I've been with EEE for more than 30 years. So I'm sure some of you who were here about 30 years ago, I was the one teaching communication engineering. So some of you may still remember me, but I'm getting much older, 30 years old now. So maybe I need some kind of fake, deep fake to change my face. Anyway,
we can detect that.
Yes. Anyway, so I'm really happy to have an opportunity to speak to our EEE alumni. I hope that with this platform, we can meet again in the near future. So today, let me share the screen. So today's topic is seeing, believing. So it's straightforward. Do we believe everything we see, or what should we look out for? So this work, the success of this work pretty much in this area for my team, coming from my former PhD students, Chao Hong. He's currently in Ernst & Young as a scientist, and Khosrow, a scientist in Apple USA, and Fan Jiayan is a professor in Fudan University, and Li Haoliang is professor in the City University, and currently Ling San is the postdoc in Rose Lab. Without them, I won't be able to sit here to give you a talk because of their contributions. Okay, let's look at some of the photos here. You see, these photos are quite famous photos. There are 6 of them here. Now, if you look at it, you can't tell there's anything wrong with these photos, but in actual fact, these are all fake photos. Like the first one, like Lebanon War, appeared in Reuters 2006. And the original photo, there was no such heavy smoke at all. John Kerry and Jane Fonda, these photos are a spike photo, meaning that both are taken in 2 different times. One in 1971, one is 1972. And because of the political motivation for when John Kerry was trying to run the presidential campaign in 2004, and you know, as if he is against the Vietnam War. Now, the snowball is another very interesting story. So it was reported in NBC Tonight Show and ABC Good Morning America. So they're showing this photo and say, wow, where on earth there's such a big cat? You know, after this show, the owner came out and saying that, well, actually it's a fake photo. His cat's only 21 pounds. Right? If you look at the National Geographic, right? You look at these 2 pyramids. If you go to Egypt, whatever angle you look at it, you'll never see such 2 pyramids so close to each other. What about President Abraham Lincoln? Right? If you look at his photo, everything looks fine. But in actual fact, the Lincoln's body is borrowed from the body of Southern politician John Calhoun. So in the history, you see these 2 photos at different times. So this problem of manipulating photo has happened for a long, long time. So of course, there's some image forensic photo that for fun, and you look at them, you really can't tell they are fake, you know. Now, so it's seeing, believing. So that's why we're looking at image forgery. We want to see if the image is really manipulated and if human can still trust images that we see. So when we look at forgery, basically we can look into different type of altering, like objects, related objects, splicing, enhancement, retouching, morphing, or cropping a photo, or put a false captioning. And those created from scratch, right? When you watch some movie, their computer graphics or animals, sometimes you really can't tell it's real or fake, even for painting itself. So for this scenery forgery, recapturing, right? People say, oh, I've been to Hawaii, show a nice picture at the back, but maybe they never been there, all right? So, or a mixture of artificial display versus the real display. So it's a mixture of that. So these are all forgeries, some type of forgeries. What we are focusing more on, those images, with the purpose of misguide or deceiving others. That's an important part. Now, this one, it shows the Israeli cabinet photo on their website. As a matter of fact, the original one are the one with two ladies there. So for whatever reason, these two ladies were replaced with the guy here and another person somewhere here, this person being put here. That's one actually in the website. Now, captioning, this India newspaper report a tsunami. But the photo, they put it here, actually coming from a photo taken from Jintanjiang River. So nothing to do, it's just a big wave, nothing to do with tsunami. Right, another case is some terrorist attack in Luxor, Egypt. So, and the reporter, you see on the right-hand side is the original photo, the reporter make it more graphics, right? Put it into red as like it's all bloody, red bloody, right? Again, it's an enhancement. Now, you look at this, another photo here. This photo, you see the Iraqi soldier and then a US Marine, right? Giving him to drink water. Looks like very nice. But if you look at this part, if someone show you this part photo, it's very aggressive, right? The Marine was very aggressive to the soldier itself. But they all come from the same photo. So it all depends how a photo being cropped and how manipulate people to believe in one way or the other, right? So it tells you very different messages here. Now, this is another famous one that appeared in the Straits Times 2008. And this happened in Beijing. So what happened is that someone has a cardboard of a South China tiger and then put in the real bush and took a picture of it with this picture and tried to apply for a grant. Say, okay, to look for this South China tiger, if they're distinct or not, right? If what happened to them. But actually, they have not seen this for decades. So again, they found out this is actually a real scenery versus a fake one. So again, there's a try to deceive people. And this commonly, we see this kind of object deletions. We have one little boy being removed from the photos, right? If you look at these two photos, you can't see any things unusual here, right? Another thing is like the change of the color on the left-hand side. On the right-hand side, they're identical photo, except the car color has been changed. So nobody knows you own a red one or you own a yellow Ferrari, right? Now, because of all these new image tools that we can use, right? So that create all kinds of images of videos. So because of that, it attracts a lot of research work in this area. The research work can be related to source identification, what kind of camera or camera being used to take those photos, or the temporary discovery, or is there anything hiding there? We call it stagno analysis. Or can we recover the processing history? Or how can we compare real photo versus computer graphics? Or natural photo versus retaking photo? Or device temporal forensic, or even spoofing? So these are the current works that people looking at forensics. Now, some of the ways that are being proposed, even back in about 10, 15 years ago, is okay, very simple. When someone take a photo of you with a light source, your eyeballs will have reflections. If someone's standing right next to you and taking a photo at the same time, and then the eyeball, the reflection are at different angles, right away, you know that there's something wrong because you must have the same light source coming together. So this was actually done in about 15 years ago. But the problem is that it's very hard to locate this occluding surface region to handle this, and also the lack of large-scale tests. So this approach doesn't really very useful, right? The other one, we all know that in a camera, at the back of camera, we have all the sensors. So sensors must have some kind of noise itself, right? Because all these are hardware. So we call those a pattern noise. In particular, those we call photo response non-uniformity noise. And then when you look at them, it's something like this, okay? Something like this in your camera. So what does it mean? That means each and every camera has its own signature, if you can find this noise pattern to identify what camera it is. Now, this kind of discovery is very useful. I give you a slight example here. This example is what happened is that in New York City, right? In New York, so a kidnapper took a picture of the victim and sent this digital photo to the family and asked for ransom money. And eventually, the police got hold of this kidnapper, and his home, they found a digital camera, but there's no photo in there. So they were trying to figure out if the photo that the kidnapper sent to the family, is it coming from that camera? So what the scientists help the police to do is that, okay, they get hold of the camera and take a bunch of photos, and these photos go into some filtering, we call it denoising filtering. The whole idea is to get the noise out of it, the noise residual of it, and take an average of it. So this noise residual coming from this camera. This noise is like PNRV I just introduced to you. Now, and then they use the digital photo that was sent to them, and then go through the same filter, and then they get the noise pattern, and they compare these two noise patterns. When they are very close, then they know that this photo about the victim photo must be coming from the camera from this kidnapper. Indeed, it was. In this case, this was used as evidence in the court against this suspect. So this is a real case happening. So this is something that actually being used in real world. Okay. So now, what if we don't have the camera? So we only have the photo. Can we tell anything or not? Well, let's get back to something related with this demo-seeking technologies, right? So at the back of the camera, all those sensors, each sensor correspond to each pixel. So each sensor is capture only one color. So it has this what we call this color pattern, like a green, red, and blue color. So green, red, and blue color that will create the photo we call raw image, right? Raw photo. And if you look very carefully, the raw photo has only 3 colors. So each and every pixel, there are 2 colors missing. 2 colors missing there. Because of that, sorry, let me just turn off this first. Because of that, right? Okay, sorry about that. Because of that demo-seeking, that we know that every single camera, the camera manufacturer, when they produce the color images, they have to use this demo-seeking process. So each model with one particular type of demo-seeking process to produce a color image. So in order to produce a color image, they have to estimate the missing color channel. If it's a green one, they need to look at the blue and the red one. So that means each one has certain way of using the weighted average of the neighboring color to estimate the missing color, right? So that means we can make use of this weightage as a feature for those particular camera models. So if we do that, right, we are looking for the missing, these are the weights that we're looking at. That will be the signature of the model of the color. So what we need to do is to do a re-engineering find the weight patterns for each based on the image we have. Okay, so if we do that, so this gives you an example here. So that's what we did. We look at this as 16 algos, different algos, right? We have 16 different algos, and then suppose we are estimating the green color. So each one of these will produce a green color, right? And then our algo, our estimate will also produce it. We compare both of them and we want to see the error. You can see that the proposed we have a very small error. That means we can closely estimate the weight correctly. So with that, right, we can see another thing here, how close we can do it. Now we know that after producing a color images, we also have this post-processing. Post-processing like quantization, color calibration, gamma correction, AWGN or color transformation, all these things, including JPEG compressions also. Now we look at each and every one, right? We look at our technique here with these quantizations, right? We can still achieve accuracy close to 100%, right? We go down and down, okay, with a gamma correction, lower than 100%. So the performance is still very good, okay, even with the post-processing. Of course, when it comes to JPEG, it depends on the compression rate. If the compression is very strong, right? Say with the Q factor close at 50%, obviously the history of demosaiking will lose. That's why the error rate will be much higher. The accuracy drops a lot. But if not, then the performance is still quite good. So now with that, what we are saying is that we can actually estimate, we can tell which camera model that you use to produce that images, right? Because of the recovery of the history. So because of that, we can do an experiment here. We do a camera identifications. So we have 14 different cameras. We have 2,800 JPEG photos, and each photo we chop into 12 small ones. And then we want to test them to see which one come from which camera. So if you look at the confusion matrix, now we have 14 different camera here, which is this here, and then 14 predicted one. So if taken by the first camera, can we predict that it is the first camera? 97.9%. Okay. If second camera, you predict as first camera is 2.7%, right? So this tells you how good it is. So on average, we can achieve 98% accuracy to identify each photo coming from one of these 14 cameras. Now, with this kind of knowledge about demosaiking history, even if you produce a raw image, say suppose you have a raw image, and then you want to use one of the software to create the color image, right? You see here, this is a color image being produced with this raw photo, raw image using different software too. By the same token, we can do the same thing also. Here, again, we have 10 different software tools to produce the color image, and we can identify them. So in other words, imagine if you send a photo to me, okay, I will be able to detect which software tool you use to produce this color image. So these are very, very useful information, right? And okay, now with this, can we use it for detection purpose, detecting if an image being manipulated or not? Just now we're talking about the source identification, which camera it comes from, right? In here, we give you an example here. We have a photo taken by Olympus, right? This photo. Now, if this photo, I divide into 4 regions. The first region, I don't change it. The second region, I shift by 1 pixel diagonally. Region 3, horizontally 1 pixel. Region 4, vertically down 1 pixel. So now, this is a tempered image, right? So I want to find out if I can detect where is the tempered regions. So that's very simple. If you look at this image, right? If I break into small pieces, because this with the weighted estimation, I find that there's no change. This demosaiking is correct, right? But once you shift it you are damaging the history. So everything here is upside down here. Everything is wrong here. So that's why in the ground truth, you know that these are the tempered region. And in our algo, and we can detect this, okay? Meaning the darker the color, the higher probability that is being tempered, the region is being tempered. So we can do it well. Even for splicing, right? Look at this photo here. Now, this photo is a combination of these two. This part here being posed on top of here. So like this one. So this is the tempered region when you use this as reference. And then this is our estimated. You look at the estimated one and the detected one versus the ground truth. So very close, right? So what I just told you is based on history of the mosaic. There are other works that are done by other researchers. So, okay, can we look at the JPEG itself, right? The JPEG itself, and it turned out that we can do that because in JPEG, right, in JPEG, if you compress a JPEG, you see that this original without compression, okay, you look at x-axis are the DCT coefficient value. On the y-axis is the frequency, okay? And then you can see this kind of a distribution. But if you compress one more time, you have a different, because of quantization, you miss it. Now, that's when you align it properly, you see this. But if the alignment is not proper, right, in the JPEG compression, you can see the blocking artifacts, this blocking artifact. So these are all the information you can tell. Imagine if you have two photos, one without compression, one with a Q factor of 90 or something. So you want to cut from one photo and paste on our photo, your original photo will have two different Q factors, right? So because of this information, this group would be able to tell, you see, this car is actually not in the original one. So it can be detected based on these two types of features. Now, we look at that there a lot of work has been done very well in terms of different types of manipulations, right? And but what about when we change the brightness only? Say, for example, in this photo, right? These two photos are identical, but the brightness is changed. If somebody say that, oh yeah, I was in the bridge in the evening, okay, it's dark, right? Or maybe they are actually in the morning, right? But if they produce a photo is a nighttime or dark time, it will be changing of the brightness, right? How can we tell which photo is original, which photo is fake? So we said, okay, we were the first one looking at the EXIF. EXIF is like the header for each photo. As a matter of fact, when you look at your photo, right? You look at your iPhone photo, and then there's an information. When you touch the information, it will show you, information like this, like ISO speed, exposure time, F number. Now that is very interesting. Why is interesting? Let me show you this example here. We have black and white here, which is ground truth color. When you use a camera to take a picture of this black and white, right, and different setting, this one is ISO 800, this one ISO 3200, this ISO of 12,800. And the outcomes look very different of the same photo, okay? So you can tell the EXIF file, those parameters in EXIF actually associate with the noise pattern. So if we can find this correlation, if somebody make change of the content, then it's not going to correlate it with the EXIF parameter anymore. Or if someone tamper with the EXIF parameter, it's not going to match with the content itself. So we make use of this concept to do this. And then it worked very well. What we did was, well, we use 3 different cameras, each one take 400 photos. So we have 1,200 photo itself, right? With this photo, then we did experiment here. So we want to test the brightness based on the aperture, shutter speed, and ISO value. Look at the true positive, true negative, Now, even for aperture, we can see when we increase the brightness, we can still detect it, okay, based on the aperture. And when we decrease the brightness, we can still detect that if there's change in the brightness or not. So that's why at the end of the day, we have very high accuracy compared to other work with much higher accuracy. We also can use the same thing for the contrast detections also. Now, people may ask, oh, okay, what if I have a photo from a totally different camera? Would you be able to have the similar correlation? Yes, it's the same because of physics. So we did that. We used the models, the Canon and Olympus, to do the modeling, right? The regression analysis, and we used the Sony photo to do the testing. Look at the accuracy for testing if the brightness has changed or is tempered or not, right? We can get all of them get close to 100%, regardless which combination you do it. So that means it works without knowing the camera source. Now, coming back to these 6 photos. So what we did was look at the aperture value. So in A and B, it shows the X shows that, okay, the aperture is 5 stops. But our predicted one for A is 5.7, for B is 13.8. You can see that there's a big difference between the two, small difference for this one, big difference for this one. That means A is questionable, right? If you look at the rest, you look at this, right? This 4 to 5 and 10, 5. Again, this is questionable. Same as this one. This is closer. This is the same. We can also look at the shutter speed, ISO also. Based on all this input, very easily you can detect that B, D, and F, the content noise does not match with the exit file parameter. So that's why B, in actual fact, B, D, and F are the manipulate photos, manipulate images. Okay, now our work, right, in 213, we did in 213. So, and we're the first one using exit header to do it. And in 2018, the CEPR 2018, UC Berkeley, a group in UC Berkeley, used the same idea, but they extend out and use the deep learning to solve the same problem using exit metadata. And of course, because of deep learning, they have improved the performance. Anyone interested can refer to their paper, and they're working on this for fake news. Okay, so now we talk about the mosaicing. Okay, we talk about EXIF, we talk about the PNRU noise. Now, what about when we look at the sharpness issues? So look at these 2 photos here. Now, this photo, when it's taken, obviously the sharpness will be different, right? The sharpness of 2 photos cannot be identical. So if this is spiced and this part is put into here, you generate a new photo like this one. And then somebody got this photo and resize it and make it resize it like this one. Now, many existing techniques those days were not able to solve that, to tell that it is a forged or manipulate photos. So we develop a sharpness base. We basically look at the sharpness. Okay, there's change in the sharpness here. We do some sharpness measure, and then we'll be able to detect the edges where the 2 part joins. Right? So, and this one works very well also. And then it turned out that the speed compared to existing technique, right? Accuracy, we're better, right? Our proposed method is better. In terms of computational time, it's much, much shorter also. Okay, this work. Now, so that's one way to look at the sharpness. Another way is also interesting. We said, okay, say suppose you have 2 photos. One photo, and when the person is taking the photo, usually there may be some kind of mild hand shaking, right? So that introduces motion blur. Or the photo itself may also because of slightly out of focus. So we have this out of focus blur here, okay, out of focus blur. So if someone tried to put this car into here, so end up with that, you have a region of out of focus blur and you have a region of a motion blur. It's a combination of both. and then you end up with this photo. So many techniques at that time was unable to solve these problems. So what did we do? Well, we look at, hey, interesting, this problem, when we look at something called blur kernels for our focus and motion blur, and there are two parameters. We call a sharp parameter and also standard deviation parameter. We look at the distribution of these two parameters, okay? We look at this is the sharp parameter value, and this is the standard deviation value. And it turned out that for our focus, the standard deviation value does not change much, but the parameter, the sharp parameter change a lot. And for this one, the reverse. So these are two very distinct categories that you can easily separate them. With these two features, we are able to separate this to tell if the region is motion blurred or out of focus blurred. Give you an example, this photo, right? And when we look at every boxes and to see if there's a motion or out of focus, then we are able to see these two regions, and it turned out that this region is motion blur, and this region is out of focus blur. So you can tell that it works well. Okay, so what about if a photo recapturing? So for example, if I ask you these two photos, can you tell which ones are from natural scene and which one is actually recaptured from a photo? Very interesting. So we did this in a 210 as a matter of fact, okay? And we used a final year student to work on this problem. So at that time, and then we took a 2,700 photo. We create 2,700 photo coming from what? Captured from different cameras and then display on different display. We capture from the display itself, okay? And these are the photo like this. Then we did an experiment with a human. So we have 50 test photos and asked the human to see if they can tell it's a recapture or original. And we did some training for them. We tell them, oh, okay, now this original, when you do a recapture look like this, original recapture look like this, right? So what's the outcome? Well, we have 20 of them original, we have 13 of them a recapture. And it turned out that when it's recapture, right, human cannot tell the difference. It's 50-50. They cannot tell it's original or recapture. So we did that. We used the machine to do that. So we have hand-picked features here. We use these three different features, which I won't go through the details, right? Use these three different features and use the traditional approach to do the classifications. So, and then we were able to look at it with a 0.5% equal error rate, very accurate. So we can tell that at this time, a machine really beats human in identifying recapture photos. Really big differences. Well, that's in 2000. We did not know that, wow, after 10 years, we don't know that people are very interested in this work. Why? Because when it comes to Alipay, right? Alipay, what they do is that they capture your face. And then with your face that they authenticate you. But then the problem at that time was that, what if someone take a picture of your face and then use your face to get access to transaction, or replay the video, or this kind of thing, or mask, all these things, right? Oh, this is actually the recapture problem, isn't it? So recapture problem, so we were able to solve it. So the problem at that time, very easy to solve, very good performance. But the problem here is this: when you have a very similar environment to do that, right? The performance is excellent. But when you do a training on one data set and then you are trying to test it on a different environment, the performance is very bad. So what we are trying to do at that time, not long ago, and we look at domain adaptation. Basically, you have this source domain that's available, and then you do a feature extraction, all this thing, you get a mapping learning. And then a task domain data, right? You do the same thing. Then you try to do some kind of a learning between these two in order to tell the differences. So that's what we did. And then you see what happened. Now, you have different methods being used here. And here you use one data set and and for training, another data set for testing, different data set training, testing, training, testing. If you don't use domain adaptation, that's your performance. If you use domain adaptation, you can see that there's improvement, right? 33%, right? Those are improvement. You can see the error drops, right? So error drops. But then, okay, we said, okay, we have done a good job in the domain adaptation, but this is no use, in a real application. I mean, it's still the error is too high. So because of the RGB images, they are very badly influenced by lighting. So that's why we have to use a multimodal RGB plus the infrared camera to do the job. So I play this is one of the work that we did it for a company, and then for that to use
in this video, right? We are going to
let me cut this short here.
System is embedded with both RGB and infrared sensors and is equipped advanced detection model based on a novel artificial neural network, which can detect various presentation attacks effectively and robustly. Here are some demos. Our system can detect the printed face attack in both RGB and IR images. For the well-printed 3D face statue, our system is also robust enough to categorize them as non-human face. For the challenging 3D printed face mask, our system is also able to differentiate the actual human face and face mask. For the partial face occlusion, the system we developed can also detect both the mask covering the eye region as well as the conventional mask which covers the nose and mouth region.
So this actually being used in a few banks in China. Let me ask you a question here, right? If you look at this this animal, everywhere you can tell this elephant, right? Now I show another photo. What I do is that, okay, I put some noise into this photo and generate a new photo like this. If I ask you, what is this? Everyone tell me it's an elephant. When I blow up the noise, these are the difference. These are the noise, right? Being added into this photo, get this one. And I ask you the same question for this one. Everyone tell me that, okay, this is the what called the schooner, right? So, but if you use a machine, right? This day, if you use a machine to do, right? They will tell you this is a Corolla, and they will tell you this is an iPod. So you can see, in this case, a human actually beat the machine. So you see what you see is what it is, right? The machine will tell you something different. This is another big research you can see these days. A good example is like a stop sign, right? If someone do some kind of training to do it properly by putting something here, right? The machine will predict this is a yield sign rather than a stop sign. So you can imagine, right? A machine has no intelligence here. They thought that this is actually very clearly a stop sign and say that's a yield sign. So that is the problem these days. So that's why it create a lot of research work in this area. Now, another thing is that I want to mention about another thing is that the time is running out very short. So about the forgeries of something about videos, right? So usually the videos, when people do the manipulation, usually they decompose a video in a frame by frame, right? Extract the face, manipulate the face frame by frame, and put them back together. So what they're doing is two things. One is either face identity swap, sometimes well known as deepfake. So replace entire face of a target person video with the face of source person, like this one here. This person, this face replaced by this face, you end up with this face. Or we call the face action reenactment, right? So you just look at the motion of this one. So this is original face, and then look at this motion, mimic this motion, end up this. So the most recent one is the deepfake video showing the Zelensky telling Ukrainians to surrender. Is the most famous, only about, I don't know, a few 1 week ago or something. So you can, if you look at the video, right, you really can't tell. You really cannot tell it's a fake one. So, and also there are a lot of deepfake challenges that you can see. You can look at it.
You could have like this
right.
pool,
For example, on the left-hand side,
like dresses and fancy dinners, and you could hang out with celebrities, and it just
right at the right hand side.
Look what you could have. You could have like this pool and these nice like dresses and, you know, fancy dinners, and you could hang out with celebrities.
Actually,
and it just
these two are coming from two different phases, right? Two different phases. Now, the interesting thing is this, okay? If you look at in detail, frame by frame for this one, you know that all these fake one, they are not consistent. The brows are not consistent. And also, you look at this one, even a non-consecutive frames, right? There's a mole in this lady, but then you happen here, this one, mole disappear. Mole here, mole disappear, mole here. So that's why these are all what we call dynamic inconsistency. So with all this inconsistency, you can actually detect this kind of fake videos also. Now, when we talk about fake video, usually come with audios, right? So usually they separate these two, the video and the audio. They look at the deepfakes for from the video and let audio sync detector and also audio forgery detector. With all this, these two are more related audio, and all this together to classify and then find out if it's fake or not. Again, there's a lot of research work going on these days. Okay, so now with that, well, I finish here. So the take-home message here, there are 3 points here. Number one is that in our digital world, right, can we believe everything we see? And I've shown before, not all the time. Nowadays, really not all the time. Or shall we always trust our AI-driven machine visions? I also show you a machine, AI machine, they make mistake. Even human can tell that there's an obvious mistake. So we are not there yet. Can we stop this visual disinformation, all this image and video things? Now, come to think about it, it's very difficult in a sense that because people upload things so fast into the internet. So you get a lot of fake news based on all this image and video. Perhaps we can go back to this watermarking. See, watermarking, when we started watermarking, is really for copyright protections. So in other words, if I have a piece of art, I put a watermark there. If I have a movie, I put a watermark there. But who wants to put noise into this kind of thing? So people will avoid doing this, right? And also, if you cannot 100% secure, then the movie is, you know, there's a lot of money involved. So that's why it didn't work well. But now, if we put a watermark, say for Washington Post, okay, put a watermark, all this they send out, then we call this is an active approach for this detection. This may be what we have to do in the future because of, you know, there's so many information being put into the internet. So with that, I will end my talk, and thank you very much.